Alrighty, so start of chapter 9 is just like intro stuff, and this stuff is honestly just like things you have to memorize. So NMR,
Yeah.
just know like the general gist of it. You don't have to know everything he said in class because he's just very, very passionate about NMR. So kind of just know that you put molecules in an electric field, you put a pulse in the electric field, and you figure out what the resonance frequency is. That's all you have to know. And then now we've done 3 different types of spectroscopy, so I will add that here for you. NMR tells us the structural framework, IR tells us functional group, and mass spec just tells us the mass, which we can use to figure out the formula. Ta-da. So, as far as the exam goes, you will have NMR questions and mass spec questions. He might give you a question that's like, oh, what type of spectroscopy would you use to tell the difference between these 2 molecules? But you're not going to have a question that's like IR. Like, you won't have any IR on the exam. So that's kind of good.
So mainly mass spec and NMR.
Yeah, so like he might give you a question like, he gives.
Oh yeah, okay. Yeah, he didn't really go over IR that much.
Yeah, it'll just be something like this, right? And he'll tell you, what kind of spectroscopy would you use to tell the difference between these 2, right? And you would have to pick between NMR, IR, and mass spec. And what do you think we would use to tell the difference?
NMR?
So we could use.
No, the formula, so it would be mass spec. Right?
Well, okay, so technically, I guess you could use NMR and mass spec, but the best one would be IR because the biggest difference here is the functional group.
Oh, okay.
So we can do another example. I know he did one in his PowerPoint, but that one was like honestly just too complicated. So I'm just gonna make a new page right here. Chill. Oh my goodness. Okay, so let's say I have that same molecule that I had the first one versus this, right? So the idea behind it is the first thing I would look at is what kind of substituents we have here. So we have an alcohol in the first one, and we have an alcohol in the second one. All right, cool. So now what's the difference? Well, this one is connected to a carbon that's connected directly to 1 carbon. So we're going to call this primary. And this one is connected to a carbon that's connected to 2 carbons. So this one is going to be secondary. And we have in total 1, 2, 3 carbons. 1, 2, 3. I wanted to make that the same. So we're going to keep it as 3 carbons. So we're going to say that the mass between these 2 is the same. Hello, Leah! And we're going to say that the functional groups are exactly the same, right? So the only real difference is that this one is connected primary and this one is connected secondary. Oh, also hello, Evelyn.
So would that be framework?
My day has been a day.
I saw in your email. But yes, to answer your question, the framework is the difference. And so that would be NMR. Now, let's say we had this versus this. That's the one I had before. And just in case, because I know we went through it kind of wobbly, I don't know, whatever. So you said mass spec and NMR, and you are technically correct. You definitely could do mass spec because those two have different masses, right? But it's such a tiny difference that that's not the best technique you could use. For the same reason, or I mean, NMR is kind of the same explanation, right? So both of these are in the heteroatom region, and the difference is just one hydrogen. So we have 1H versus 2H. So again, that's a super, super tiny difference. Whereas IR, there would be a huge difference because it's two entirely different functional groups. So the biggest difference would be in functional group. So for this one, we would use IR. And again, IR is just like the best answer.
Okay.
And then if we had something like this, right? Now, we couldn't really use IR because it's exactly the same functional group, so we throw that one out. We definitely could use NMR, right? Because there's so many more carbons here. But also, the mass spec is going to be wildly different. So, we can say the mass and the structure. But they're both primary alcohols, so it's not as much like the structure as it is the number of carbons. So I will put that in parentheses. So for this one, we could use mass spec or NMR. And those would be equally valid answers, in my opinion. He won't give you one that has two correct answers, but I just wanted you to kind of see the difference.
I don't know if anybody else wants another subject, so.
Yeah, so a couple people just came in. So hello, everybody. I was going to say, like, hi, Tony, but I really am. Is your name actually Tony Montana? Because that's really funny. I cannot hear you.
Oh, hello.
Oh, hello.
Yeah, so it's Anthony Illumin, not Tony Montana.
Ah,
Just
okay,
like-
okay. That makes sense. I was like, that's funny. Um, all right. So for everyone who just joined, we were kind of just going through the exam review one more time and kind of looking at all the concepts. Does anyone have any specific content they want to work on?
Yes.
Okay.
Uh, I would like the chapter problems for number 14, please.
Okay. Let me open up a new set of practice problems because the one I have is like all written over. So give me 2 seconds. And while I do that, does anyone else have anything specific? I can't look at the chat right now, but if you put something in the chat, I will look at it in a second.
Is the exam just chapter 9 and 11?
So it's mainly 9 and 11, and then there's a little bit of chapter 12, but like he kind of mixes chapters 11 and 12 together.
Mm.
So yeah, it's gonna be. I have a list.
So pretty much like everything he's talked about in lecture up to this point.
Yeah, pretty much. It's gonna go through NMR, mass spec, alcohols, oxidation reduction, and Grignard.
Okay. Also, I wasn't able to attend the exam review last night.
Yeah, it will.
Put it on YouTube. Yeah.
It's okay. So part 1 is like uploading right now, and then I had to cut some stuff out of part 2, so that'll be up in a little bit, and then there's a tiny part 3, that shouldn't take long to upload, but I do want it to be in order, so by the end of the day, for sure, it'll be up.
Gotcha.
Create a new note, please. All right. Let me close that so I can see you. Also, I am recording this session so that you guys could watch it back later. If anyone has any issues with that, just let me know. Okay. And then if you guys have any like specific questions you want to go through as we move through this, you can either put them in the chat or tell me. I will most likely forget if you tell me verbally, so you will have to remind me if I don't go over it. I know, Anthony, you wanted to go over number 2 yesterday, and I forgot. Do you want to go through it really quick before we go to 14?
Yes, awesome. Thank you.
Okay. So, alrighty. What you always want to look at is, for NMR, is symmetry, right? That's the first thing we're always going to look at. Does this molecule have any symmetry? Yes, it does. So we're going to have symmetry right here. And Leah said some in the ring, and yes, that's exactly true. So this part doesn't really have any symmetry, but we have some symmetry in the ring. So I'm going to go ahead and highlight each unique signal. So this one is unique. It's by itself at the end. This is going to be one signal. Those 2 carbons. These 2 carbons are going to be one signal. This carbon is not going to have a hydrogen signal because there are no hydrogens here. We have 4 bonds. The next signal is right here. Oh, just kidding. Hold on. And the last signal is right here. I thought we were counting signals, but that's not what the question is asking you. That's why you should always read what the question is asking you. But in case anyone was having trouble counting signals, we do have 1, 2, 3, 4, 5 H1 signals. All right. Now, specifically, we're looking at these ones, and you want to find the chemical shift and the multiplicity. And we know that I am going to redraw it just because I like looking at the hydrogens this way. We know that we have to be within 3 bond lengths in order to be considered a neighbor. So we're going to look at this 1, 2. Oh, we ran into an oxygen. So we can't really go through it. They decided this semester to say that you can go through it sometimes. We're going to ignore that. Even if we did go through it, it doesn't reach another hydrogen. It just reaches a carbon. So these guys are singlets, which means we can get rid of this choice and this choice. And now we have to look at the regions. So Leah said 4 ppm. So our answer choices are 1, 3.4, and 4.5. So it is going to be around 4, but we have to think of it a little bit more specifically than that. So we know that the hetero atom region is 3 to 5. So we can already get rid of this one because 1.1 is way off. And when we're looking at the 3 to 5 region, I believe the reason Leah said 4 is because I told you guys that in this region, a 3 is going to be a nitrogen, a 4 is going to be an O, and a 5 is going to be a fluorine. Right? And so, Evelyn gave an answer and then she said, oh, nah. Don't doubt yourself. Don't take back your answer. You might be right. We're just going to go through it step by step. So anything that's like an OH is going to be right around a 4. So something that looks like this, when it's 1 carbon away, is usually going to be a little bit less than 4. and so on and so forth. So in this example, I would go with 3.4. Exactly. And then like Leah said, just to reiterate, it would be a lower number because the H is connected to a carbon, which is then connected to an oxygen. It's not directly connected. Perfect.
So if it
now,
was directly connected,
so sorry, go ahead.
Rosemary, so if it was directly connected to the hydrogen, then it would be 4.5.
So in this example, it would be like right around a 4. I mean, in general, it would be right around a 4. In this example specifically, the reason he gives you 4.5 is because these hydrogens right here are in the heteroatom region, but they're also right next to a ring. So these would be like extra de-shielded because of the aromatic ring. So those hydrogens, instead of being around a 3.4, those will be around 4.5 because of the extra de-shielding from the aromatic ring. So an OH would be right around a 4 if it's just by itself. There's nothing else on the chain. And then if we have an extra de-shielding group, it might be a little bit above 4. Does that sort of kind of make sense?
Yes, it does.
Okay, cool. All right, so let's go down to 14. Okay, so predicted splitting pattern, and we're looking at proton C4. So C4 just means carbon number 4. And now we have to, whoa, I don't know what happened. There we go. We have to figure out which one is carbon 4, right? So we can either number this way, or we can number this way. And just remember, these two methyls are exactly the same. These two methyls are exactly the same. So this could be 4, or this could be 4. This could be 1, or this could be 1. The only reason I did this is so we're not looking at a huge mess, if that makes sense. So would we choose the green numbering or would we choose the blue numbering? We got 1 vote for green.
Green?
Yes, I definitely agree. And the reason for that is because we want the biggest or highest priority group to be on the smallest number. So this would be on number 2. The methyl would be on number 3. That's more preferable than this being number 2, this being number 3. So now that we have that figured out, I am going to redraw this just so it's a little bit bigger. And we know we are looking at carbon number 4. So I'm going to draw those hydrogens, right? And what is the first thing we always look at for NMR? Symmetry. Cool. So we have some symmetry inside the ring, and we also have internal symmetry here. And I forgot to draw one of the carbons. And here. Right? So right off the bat, we know that all 6 of these hydrogens are exactly the same. So they cannot split one another. We know that these 6 hydrogens are the same, but they're really far away, so we don't care. And I'm going to draw out this hydrogen right here. So we're going to go 1 bond length, 2 bond lengths, 3 bond lengths. The only thing we reach is the pink hydrogen. So we're going to say we have 1 pink neighbor. plus 1 would give us a doublet. So I would pick, oopsie, doublet. How do we feel about this one?
Great. I was counting the wrong direction. Then I forgot about IUPAC.
I feel that. That's what I figured most students would do because, like, it's really a 50-50 if you don't remember the naming rules.
Where do you get these problems?
So if you are in Dr. West's class, they are on Canvas under modules. And if you are in Dr. Roche's class, I sent them to you as an email a couple days ago. And if you can't find them in your West class, I can show you where to find them on Canvas.
Good.
Okay.
Just blanked out.
I
I already have these.
Oh, you do? Okay, good.
I already did these, and I'm like, was this like graded? I'm sorry.
No, it's
I'm sorry.
totally fine. I get that. All right, so let's right quick. Sorry, 1 second. Something popped up on my screen, and I was like very confused about it. Okay, cool. Yeah, I was uploading the videos, and it like popped up, and I was like, which video is this? I'm very confused. And okay, so Sarah asked, are all the blue ones one signal? Yes, exactly. So since this is symmetrical, all 6 of these hydrogens are one signal with an integration of 6. And we would have the same thing over here. So 1, 2, 3, 4, 5, 6. Yeah, so we were only looking at C4, but that's kind of where the trick is. So C4 and the substituent are the same signal. So, like, if they had been closer together, okay. Yeah, the trick is just that, like, whichever one of these you chose, the answer would be exactly the same because they are the same signal. That's how I'll say it. All right. Let's see if there's a similar one to this. Okay, I want to do this one. So, I'm going to let you guys look at it for 1 second. And then we're going to talk about it. I'm very tired today, so if I'm talking like really slow, I apologize. I can't even. My brain hurts. All right, so I am going to draw it out again just so it's bigger and I can write on it. So we are looking at these hydrogens right here. And if we look at, sorry, that was funny in the chat. No worries. So if we're looking at symmetry in this molecule, we can see that this guy and this guy are actually symmetrical. So all of these signals, or all of these hydrogens, are one signal. And Leah said that she thinks it will be a 3 ppm singlet. And I definitely agree with it being a singlet because 1, 2, and then we have this nitrogen here. We can't split it. So it will be a singlet. We can get rid of this, 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 this. Wow! No other thinking to be done. It is a 3.0 singlet. Yay! Any questions about this one?
Just to be like 3,000,000% sure, we are not splitting through heteroatoms. Like,
So
we're not doing.
No, we're not going to split through heteroatoms unless they specifically tell you, hey, we have a pure solution. If they tell you that, then you can split through a heteroatom, but they're not going to do that. Dr. West said they're not going to do that to you.
Okay.
Okay, cool. And yes, I can definitely show you how it's a singlet. So the blue that I'm about to draw on it is going to be like counting the bonds. So we have 1 bond here, 2 bonds here, and then we're stuck. So it cannot reach any other hydrogens because 1, we have a heteroatom, and 2, even if we didn't, neither of these directions would reach a hydrogen. Therefore, there are 0 neighbors, which makes it a singlet. You are so very welcome. Okay. Does anyone have any practice problems they want to go over, or do you want me to just kind of go through and pick whichever ones I think are good examples?
Can we do like I guess like applications? I guess they're in the 30s.
Yes, so like the ones that have the spectrums, like this one.
Yeah.
Yeah.
There we go.
Like I was looking at one.
Mm-hmm.
Yeah.
Okay.
Whatever one you choose.
I'm just gonna go in order and we can do a bunch of them until you guys feel confident. So, I have kind of a specific way of going through these. It's not super specific, but, you know. So, when I look at this, the first thing I think is 1, 2, 3, 4 signals. So, I know right off the bat that I'm looking for something that has 4 signals. So, I'm going to zoom in here. And let's go through each of these and find out how many signals they have. So symmetry, symmetry, symmetry. We can see that these 2 are symmetrical, so we have internal symmetry. So I'm going to say we have 1 signal, and that is the same as this one. No signal here because there's no hydrogens. And then we have 1 signal here, 1 here, and 1 here. So total of 4. Okay, we can leave this one. Number 2, we have symmetry here. So this signal is going to be the same as this signal. We have a signal here because we do in fact have a hydrogen. Bam. And then 3, 4, 5. Too many signals. So we're going to get rid of this answer choice. Next up, there is no symmetry, so we're just going to go left to right. 1, 2, 3, 4. That one could be it. Next up, we have symmetry right here in the middle. So we have 1 signal here, 2, and that one is the same as this one. No signal here because no hydrogens, and 3. 3, that's not enough. Get rid of it. For this last one, he likes to try to trick you. So this almost looks like it's symmetrical, but it's not. So we only have internal symmetry. So again, let's go left to right. 1 signal, 2 signal, and that's exactly the same as this one. No signal here because there's no hydrogens. 3, 4. Okay, so we got rid of 2 of the answer choices just by counting signals. So we have a great place to start. The next thing I would do when I look at this is, 1, I can see that this is the alkyl region, and this is the heteroatom region. And the next thing I see is that this has an integration of 6. So we're looking for a signal that has an integration of 6 and is in the heteroatom region. So here we have 1, 2, 3, 4, 5, 6 are these green hydrogens in the heteroatom region.
Yes.
Yes.
Yeah.
Because they are attached to a carbon that's attached to an oxygen. So this one could be it. But let's check these just in case. 1, 2. So the only heteroatom region is here, and it's a 2H signal. So this one is out. And last one, we do have a 6H signal here, but is this in the heteroatom region?
No, it's in the alkyl region.
Yes, and the reason for that is it is attached to a carbon that's only attached to a carbon and other hydrogens. So this one is also out because those would be in the alkyl region. So we know that our correct answer must be A.
I have a question.
Yeah, what's up?
So normally I don't do that. I kind of just looked at the multiplicity of all of them and kind of just started like doing process of elimination. So like, for example, like I don't know, like you can't have like similar multiplicities. So like, for example, like for the bottom one, even though like they share the same signal, like the multiplicity for like the other ones are off because like it's just not the same.
Yeah.
So is that like a bad way of doing it?
No, you could definitely do that. I just feel like these look so messy and they're hard to read. So
Yeah, that's true.
I personally prefer to just do whichever one pops out at me first. But if multiplicity makes sense to you and that's like the easiest way for you to do it, I'm not going to say don't do it. Don't do it. I said that kind of weird.
Gotcha.
But
Thank you.
you're very welcome. Okay. So let's go on to this one, unless anyone had any questions. I don't remember if I asked.
Yes. So, Rosemary, there was this in lecture yesterday. You were saying, so if we have the cases where we can't do the Grignard reactant creation. So if we have like the acidic H, okay, we cannot do the we cannot make the reagent, and therefore we have to protect the part of the molecule with the acidic H so that we can so that the other part, okay, that's not very clear at all.
Sorry, I think I know what you're asking, so I'm just gonna pop it up. But if I don't answer your question, please feel free to like correct me. But so we could have a acidic hydrogen either in this step or in the actual reaction, right? And so if we have an acidic hydrogen, that's basically going to make it a no reaction for the Grignard reaction, and it's instead going to turn it into an acid-base reaction. So down here, I went kind of more into detail about what exactly an acidic hydrogen entails as far as the Grignard reaction. So 3 specific conditions. We can either have carboxylic acid, heteroatom, or triple bond. So if you have something that looks like this, or this in the actual Grignard reaction, it's not going to happen. It's just going to be an acid-base chemistry reaction, just like I have drawn here. So it'll just steal the hydrogen. Or if we're, like if the acidic hydrogen is popping up in the forming a Grignard reagent step, it'll look something like this. So we need an alkyl halide, but let's say we have an OH, right? This means that, again, the magnesium is going to kind of interact with this instead, and we would get no reaction.
Okay, when you say that magnesium will interact with H, you mean that in the end we'll have, okay, so it will, like magnesium will take the H and
Not, okay, so I'll be I'll answer that better. So I kind of just said it like that because you don't really have to know the details, but what'll happen is the magnesium will still come in and it'll go like this, right? But now this negative charge will try to steal this hydrogen. So it'll kind of just be like that. And this will try to steal the hydrogen back. So it'll just be kind of like a back and forth.
Okay, so basically what you're saying is that when we have, okay, if there's an acidic hydrogen, the Br will still leave and the magnesium will not attach. Okay, then we have a carboanion, and then after that, the negative part will try to take the H, and then the oxygen will also try to take the H, and so therefore we do not have any reaction because nothing is useful there.
Exactly. 100% correct.
Okay. Thank you.
You're very welcome. And this
So
is
that's what happens when we have. Sorry.
No,
That's what happens when we have the making the reagent step. Okay.
Yes.
But otherwise, if we have the carboanion ready for a reaction and that is ready to go, and there is an acidic,
we would get something like this. So if we actually had something like this and we actually already had the reagent's going to come in and steal the acidic hydrogen instead of attacking here. So we would just get, I don't know what I was doing here. Go away. We would get O minus, and we would get this, and now this hydrogen would just, or the oxygen would try to steal the hydrogen again. So again, it would just be an acid-base chemistry question.
right? That makes much more sense. Okay, so now I understand that the negative charges the electrons from the negatively charged carbon will go to the hydrogen instead of the carbon on the reactant as they're supposed to.
Exactly. Yep.
Okay.
That's
Okay,
a
thank
really,
you.
really good question. So anybody else have any questions about this?
Could you explain it further? Couldn't understand it.
Yeah, no worries. So, okay, if we go back here, I'll just zoom in here so we can have a like good starting point. So the Grignard reaction is this part, right? The actual Grignard reaction. Before we do the Grignard reaction, we can make the Grignard reagent. And the Grignard reagent is essentially just a carbon with a negative charge. And a carbon with a negative charge is a very strong nucleophile and a very strong base. So it can act as either of these things, right? It can't do both at the same time, but it could be either of those things separately, right? So if it's acting like a very strong nucleophile, that means it's going to use its electrons to attack something and to attach to a molecule. And here we can see an example of that because it acts like a nucleophile, it attacks the carbonyl carbon, and it attaches to that carbon, right? So in the Grignard reaction here, like it's drawn, we want it to be a nucleophile. However, it can also act as a strong base. So if we were to have an acidic hydrogen present, instead of being a nucleophile, it'll act like a base and it'll just steal a hydrogen instead of going through this reaction. So we could say that Grignard reaction does not happen with an acidic hydrogen. And I lost my train of thought because someone said something. I'll answer your question in a second. As Leah was saying, this can either interrupt your reaction in the making a Grignard step or in the actual Grignard reaction. So in the make a Grignard step, we are starting with an alkyl halide, right? So let's say we have something like this. And let's say on the alkyl halide, we have an OH present, right? Or we could have a carboxylic acid, or we could have a triple bond. So we know alkyl halide is going to react with magnesium and ether in order to form the Grignard reagent, which is, like I said, a carbon with a negative charge. And in this case, that carbon has an OH on it, right? So at this point, this is such a strong nucleophile or base, it wants to get rid of this charge so badly that instead of reacting with anything else, it will just go back and try to steal this hydrogen. And then we'll have this as a product. We add an extra H here, and we have an O minus here. So instead of making...
This is gonna sound
Sorry, go ahead, what's up?
awesome. Why wouldn't it, like, I know we have, like, what is it? Like, it's like a intracellular or like an intramolecular reaction
Yes.
where it, like, attacks itself.
Mm-hmm.
Why wouldn't it form like a ring? Why would it just, like, break? Because I know intramolecular compounds sometimes
Great
form
question.
these rings.
Great question. So the reason it wouldn't make a ring is because it's acting like a base. So it's not actually like attaching to anything. It's just stealing the hydrogen because that's super easy for it to do. So it's not like an intramolecular nucleophilic reaction. It's just an intramolecular acid-base reaction.
Gotcha. Okay.
Okay, cool. And I'll highlight this just so you know this is the hydrogen that's being transferred.
Just to ask a question, I saw some stuff in the book, but these are like SN2 reactions, right? They're supposed to, or they're very, I don't know. Are they? Not really.
Okay,
Not really.
so not really, because it's like, okay, I want to explain this to you, but I don't want to confuse you. So if you start getting confused, just tell me to stop. So this bond that forms the MgBr bond, I tell you guys to think of it as just a negative charge because there's like this really weird thing that happens where there's like a partial bond between Mg and the carbon, and like then that's bonded to the Br, and it's like this really weird transition state. So if we have that kind of transition state, I don't think we can consider it an SN2 because it's not technically like a one and done, one step kind of thing. Does that make sense?
Right. So because it's not in one step, then it's not considered SN2.
Exactly.
Okay.
And then
Thank you.
for the...
So when do we need to know that it's considered an SN2 thing? Because I don't know. I didn't read the book entirely, but I was glancing at images in the book and reading small parts of the text.
That's fair. Okay, so the only times you actually have to know if it's an SN2 reaction is if I point it out, which is going to be very few times this semester. So up until now, the only thing that we've talked about that is important to know that it's SN2 is in the protecting groups example, and we haven't done that in SI yet. So you might not have seen it with me, but Dr. West did it in class. So if you see an alcohol reacting with PBR3. This is going to be SN2. And then he also talked about then going backwards, not backwards, but going back to an alcohol. So he gave the example of NaOH, and we know NaOH would be an SN2 mechanism as well. So yeah, these are the only ones that we have to like put SN2, SN1, E1, E2.
So on the topic of protecting groups, those so what that's doing is putting okay, so you just said that these were gonna be like protecting groups like reactions, right?
These ones, yeah. So this is part of protecting groups.
Okay. Okay, so for that, then basically what we're doing the SN2 reaction so that we can substitute the acidic hydrogen for something else that doesn't react. So we're actually taking it off. We're not just putting another thing on it so that it can block the way of the, like, electrons from the nucleophile of the other reagent. We're actually taking it off, and then we're going to do a reaction, and then after that we're going to put the OH back, the acidic hydrogen back on.
Exactly. But the only thing is, okay, so this is separate from the Grignard reaction. So you don't have to think of it in terms of like just being an acidic OH, acidic hydrogen. It's just like an OH. For whatever reason, whatever the reason may be, you either want to protect the OH and end with that, like you said, or maybe you want to have a specific stereochemistry or something. There could be 100 different reasons why you would want to use a protecting group. Just know that if you use PBR3, like you said, you're actually removing this entire group and replacing it with a bromine. And then we can do a separate step to re-put the OH back on, for lack of a better term. And if you guys want, since we haven't covered it in SI yet, we definitely can like start from scratch and talk about protecting groups, because to anyone who hasn't looked ahead at this, you are probably confused. So let me know.
Please, yes.
Yes.
Okay, cool. Right before we move on to that, I just want to ask, were we okay with this? And also someone asked, is there an SI video where I took these notes? Yes. So in SI, we talked about Grignard's yesterday, I think that was. So let me send you the link to that recording right now.
I have to go, but I want to do the SI ones. The September 8th one, it didn't have sound. Did you ever figure out if you could
So it,
how
yeah, what I'm basically going to do is I'm going to send you the mass spec video that I have on like the YouTube channel, because it's just covering that same concept. The reason it didn't have sound is because I forgot to use a mic, and that room doesn't record if you don't use a mic. So that was the issue with that.
Okay.
So here, wait. Before you go, let me just send this to you, because I don't label the SI sessions very well. Ta-da!
So for September 8th, is there no SI video?
There is a video, there's just no audio on it, so I think I put that in the like description that there's no audio. But here is the replacement for that.
The Monday, September 13th one, the one that you just sent?
No, that one has audio. That's the one where we covered the Grignard reaction. Just because you asked if it had been recorded. Yeah. The one that didn't have audio is going to be replaced by the one I'm sending right now. If it would allow me to click on it, that would be so cool. Thank you so much.
My job is to make college easier because students have a lot of fun.
Shut up. Thank you. Ads, man. I hate ads. Okay. that is the mass spec video that's going to replace the one that doesn't have audio. And I'm going to go ahead and put that in the
Perfect tip. Don't follow extreme routines. Do your own thing at Planet Fitness.
What?
Sorry.
Oh, okay, I thought that was me. I was like, what the heck? No audio.
But
So
that's
September 8th is just mass spec, right? I can't remember. I think I was there.
Yes.
But I'm
So
not sure.
September 8th was
there's
just
two
mass
things
spec.
about it.
Okay. Yeah, I was there for that, but I was just like, I'm sorry, I can't remember dates. I stuck with them.
That's okay.
Okay.
Sarah, did you have a question, or were you just? I don't know.
Yeah,
Okay.
that's fine. Yeah, because there's two without audio, so it's the latest.
Yes, that's September 8th one, and let me just look at the other one that doesn't have an audio while you were here.
That was like the first one.
Yeah, so I'm pretty sure.
I used one of your old recordings for it.
Perfect. Yeah. So here, if it would load, I'll send you the intro to NMR, and then they should also link you to like a playlist, I believe. So if you follow that playlist, that'll go over all the topics in order that I do in SI through exam 1. It goes past exam 1, so don't watch past the Grignard reaction video. But yeah, that'll cover it.
Okay, thank you.
You're very welcome.
Bye.
Bye. Hello, Joe. I don't know when you came in here, but I just saw that you were here. So hi. I am going to stop the recording and start recording again just so it's not super duper long. So everyone in the recording, adios.